Hello, welcome to the fifth tutorial demo, fifth code demo of this course. In this code demo, I'll be showing you how to download a LLM model from Hugging Face, use it for inference, and also make a short introduction about how to fine tune that particular LLM. So getting started with the lecture content. First, we'll look at the Llama 3.21b model, which is available on Hugging Face. You can check the model checkpoint. It is available on MetaLlama slash Llama 3.21b, and we'll be using this to do local inference on the model and also fine tune the model ourselves using some particular data set. So like whatever information that you want about the model can be found over here. Like this one whole entire page will consist about all the information of the model that is out there, and everything that will be like you'll require for it, like for you to run it or something like that. So there are two ways to use this model, like in two ways locally. So like I'll be sticking with the transformers library. We won't be going to VLLM and TGI. Like sticking to transformers library, there are two like use ways in which you can use this model. One is using a pipeline as a high level helper. So if you just want to use it for text generation, you don't want to do anything else with the model, you can simply do this, use this, and just by passing the input to the pipe, you can get the output out. I'll demo this in a code in a proper .py file soon enough. Another one is this method in which you can get your tokenizer and your model separately. If you like, let's say if you want to fine tune a model, then this is the way that you should go for, and not this. So yeah, that is how we can go ahead with this. In addition to that, you can also get some inference API over here. Like as you can see, if I just write uh, what is NLP and I say compute, it will take some time, and it'll okay, yeah, it'll takes a lot of time, and it'll like give you the output as it is. So let's not wait for this, but you can try this out later if you want to. This is just the API call. It won't use any local compute or anything. It'll just use your network to give the output from over here. In addition to that, I'll also introduce. Oh wait, yeah, seed generated. NLP is like, what is NLP? NLP is a set of techniques that can be used to improve communication, influence others, etc., etc. And it stopped over here because like I guess internally this API restricts like a max number of tokens, so therefore it stops very early. But yeah, otherwise, like if you want and if you can set the max tokens to a higher limit to generate a lot more tokens than this. Yeah, coming to the data set that we'll use for fine tuning, I'll just go over the data set over here as well. So the data set that we are using is a Minecraft question answer data set with over 700k data points. The data itself is constructed like this. You can see there's answer, there is question, and then there is source. So a question is like, this is a Minecraft question answering data set. What is the first statistics to decrease when a player performs energy intensive actions in Minecraft? The answer is this: saturation is the first statistics to decrease, etc., etc. And the source is this particular site. So what is useful to us is like this column is not at all useful to us. The only two columns that will be useful is questions and answers. And similarly, as there was a tab of use this model, there is a tab of use this dataset as well. And there are multiple things like dataset, pandas, croissant, and polars. So datasets and pandas is something that like that I know. So maybe like I'll recommend you to stick to those. We'll be using datasets for this code demo, but you can find other codes over here as well. Uh, so yeah, that's all. It's a data set that I'll use. And do note that the fine tuning is not like it's just a demo. It's just to how to get started with fine tuning. So please do not expect results from the fine tuning part of the code. The main objective of this code demo is for you to able to download models from Hugging Face and to run them for inference or any other task that you're wanting to do with them. So please do not expect something from like something coming out of a like from fine tuning like the model to generate results from the code that I'll provide in this lecture. There will be a separate lecture coming up for that, where we'll fine tune some a model for summarization. I guess it will be the next lecture coming up. But yeah, like just giving you a heads up so that you can like use this code in the right intent that it is meant to be used. So yeah, let's go down to the code now. Yeah, coming to the code part of it now. I'll start introducing the code. So this part is just like importing all the necessary like necessary libraries, etc. And yeah, so this part will be used to like access the model. This part will be used for fine tuning it, like PEFT, like parameter efficient fine tuning, and we'll be using LoRa for the same. Then this is a .env file. So yeah, I'll get to this shortly. And then this is a datasets file, datasets library to import the dataset that I was talking about. This is a Hugging Face hub, so that like Hugging Face, like so we can log into Hugging Face and using a user specialized token. So Hugging Face can know if whether it is like you doing it or someone else doing it. Then torch and OS. So yeah, .env files, like as you can see this file over here, like I won't be opening it because it contains the HF token that is associated with my personal account on Hugging Face. Therefore, I won't be opening that file. This is the hf.env file that is there. It through it stores the HF token, which allows read-write access to like from the hub using my account. So that is what this hf.env file stores. And load.env like essentially allows like loads this .env file, and it can allow the OS library like to get the environment variables which are stored in this. So HF token is equal to os.get environment HF token. So load.env like enables OS to run this function on this particular token, this particular environment variable which is stored in the hf.env file, and whatever this particular environment variable is associated to, like environment variable equal to some token, is stored into this variable. So that is it. Like it's pretty straightforward. Like there is no two ways of going ahead with it. So yeah, and then there is the login function. So login token is equal to HF token. So now since this HF token is associated with my account with the right permission, it will log in into the hub with this token. Ideally, I'll suggest you to have two separate tokens, which is one is write, one is read. So to download a model, like to load a data set, to load a model from a particular checkpoint, then you only need a read token. But to save a model, like to push to hub, you need you need the write token as well. Coming to the datasets part, like dataset is equal to load dataset. This is the dataset checkpoint that is there on the Hugging Face hub. Like you just copy that and put it over here. Then the print, like I'll show you how the dataset looks by printing it out. Model name, this is a model checkpoint, and in tokenizer and model we like take it separately. Tokenizer is auto tokenizer from pre-trained model name. This is the like Hugging Face checkpoint on the hub. Model is equal to auto model for causal LM from pre-trained model name. Then this is a print the model config. Now this particular code is used like if you just want to run inference on the model that you have loaded from the hub, you can like refer to this particular code. I've written exit over here because for now I'm just like I just want to demo that how a local inference works, and then like exit out completely from the code. This code is for fine tuning. I'll get back to it later. So yeah, we set our device, we put our model to the device, and then we ask our question. Like I'll use the same question I asked on the inference API. What is NLP? Inputs, we tokenize the input. The input is the question, so we tokenize that and put it to the device. And output should be model.generate. Whatever the input IDs are, the maximum that we have to cap it to, and do sample like random sampling decoding strategy. Top P is 0.95, top K is 50. You can like sampling strategy, sorry my bad, you can like play around with this. And the answer is tokenizer dot decode, like whatever the output is, you just decode it. Tokenizer dot decode output the first point of this. So this is pretty syntactic. Like the model dot generate method gives the output in such a way that output 0 contains the tokens which the tokenizer has to decode for in order to give you the English answer. And then again skips for special tokens, they just skip like end of sentence, beginning of sentence, they just skip those, don't like give attention to them. So let's run this file, and ideally, yeah, so you should get the output of the data set that we are using, the first split of the data set, like train split, the first value in the train split of the data set, and the model.config, and answer to what is NLP as generated by the model. So yeah, let's run it. Yeah, it will take some time to load and run. Yeah, so for some reason it prompted me to enter the token again, but I guess it shouldn't. Ideally, it should not. But for some reason, it prompted me to enter it again. But yeah, like ideally, you should store it in a like .env file, and like you can just copy it from there, so that's fine. Then it just token is valid and permission it is to write. So yeah, like ideally this should be the case. Token is has been saved in configured git credential helpers, and token has been saved to whatever. But and it should always load from there. But for some reason it asked me again. Anyway, so the login was successful, and this is the print data set. So this is the data set dict. So it only has one split, which is the train split. So the creator of the dataset expects us to create these splits on our own, like which is fine. Like some creators have the splits pre-made, some creators do not, so that is completely fine. The features that I have is answer, question, and source. Like as I'd shown you on the website, there were like 3 columns: answer, question, and what the source, like from where is the answer extracted, and numerons is the number of data points. Like it was 700,000, the 694,814, which is like that's the reason they call it 700,000. It's very close to 700,000. Yeah. Then this is one sample point of the data set, which is answer, question over here, and source over here. So as you can see, the first that we had see the question first where we seen was what is the first statistics to decrease when a player performs energy intensive actions in Minecraft. And so the corresponding answer is saturation is the first characteristic, etc., etc. First statistics, my bad. Yeah. Um, Now the next value that should have been printed is technically model.config, and as you can see, this is the llama config. So this is like llama 3.21b, so it has the llama config. Architecture is llama for causal LM. Name or path is the Hugging Face checkpoint, and then there are various parameters: attention bias, attention dropout, beginning of sentence token ID, end of sentence token ID, head dimension, hidden activation, and so on and so forth. Yes, the vocab size is 128k. Use cache true. Like there are many parameters that there are there. Uh, Coming to the output of the model, like the next parameter, next print statement that was there was the answer given by the model. The answer is okay. What is NLP? Neuro linguistics programming is a language-based therapy that uses principles of human. It's different. Like it's definitely not what we meant the model to answer, and since we have a different decoding scheme over here which might not be the same in the API called, like the answer varies. So yeah, that can happen. You can play out like play around with it, play around with the decoding scheme that is there, and you can explore. So yeah, this is the answer that we got for now. So this is essentially the entirety of how you can download model from Hugging Face and use it for inference, like pure inference that is there. But that is not what we usually want. So what to do? Yeah, in the code that I provide, I'll keep this over here. So just be sure to comment or uncomment it on whatever like experiment that you want to run it on. So yeah, so we usually do not want that. We usually want to play around with the model, fine tune it, uh, use it for some specific task or something like that. And for that, like I'll give you an introduction of how to fine tune the model using LoRa. Um, and in the later lectures we'll like actually like fully fine tune a model so that it works really well on a summarization dataset. Again, like I'm just making it very clear that this is just an introduction part. The main like goal of this lecture is for you to be able to download models from Hugging Face, load them on your local PC, use it for inference, and push them to the Hugging Face hub. It's the fine tuning part is not a main aim of this lecture. So yeah, let's go ahead with it now. Yeah, so first is like, we'll need to pre-process our data. Like we'll have to tokenize our entire like answer section, question section, and all that. And to do that, we map the questions are our inputs. Again, like if you want to question and answering model, the input should be the question, the output should be the answer. So similarly, the tokenizer gets the questions as the input and passes to the input directory. Targets gets like answers as the tokenized answers as the input, and then they assign it to targets. So that is how it works, and that is how the dataset map is created. The tokenized dataset, the map is created like that. These are all predefined functions. You need not worry about them. All you need to worry, like syntactical code, like I said again, you need not worry about like how they're working. They're predefined libraries. You need to follow the way that they're meant to be written. Uh, so yeah, going ahead from that, you get the tokenized data set in which the inputs are mapped to the outputs, which is question is mapped to an answer, uh, and it batch is equal to true, so it batches them as well. Uh, so yeah, coming to the LoRa config. So LoRa config is a class from the PEFT library, and you can then define the configuration of LoRa that you want it to be. So R, as you can, like as you already know, LoRa has a hyperparameter named R, which is the intrinsic low dimension. What you want to set it as: R is equal to 8, R is equal to 4, R is equal to 16. Another one is LoRa alpha, that is the weight of the low rank adaptations that are there, like the A and B matrix. How much weight do you want that to give? Like how do you want to weigh them? How much do you want to weigh them while calculating the output of the model? So that is LoRa alpha, 16, 32, anything that you want. And then this is the LoRa dropout, which is used to make the model more generalizable, make it more robust, as you increase the dropout. You can play around with these are like hyperparameters. Again, you can play around with this and like figure out what works the best for you, etc. And then model equal to get PFT model. So this model that is there earlier, I'll just name it better, just for the sake of this one liner. I'll just make it better. This is model LoRa, and this is the plain model. This is the plain model, is the Llama 3.2, which is like without any modifications done to it, as it is downloaded from the HF Hugging Face hub. And then get PFT model adds the LoRa config on top of this particular model, and the model LoRa is this Llama 3.2 model with all the LoRa architecture added on top of it. So yeah, that is what this function does. I'll just rename it again because that is how the code is written. Yeah, the next is the training arguments. So this is also a predefined class from Transformers library. So in this particular function, you define uh, all the training arguments that you want. Like for example, output directory, per device train batch size, num train epochs, learning rate, logging directly, like where do you want to log the entirety of the code, logging steps, save strategy, like at what do you want to save at each epoch, or do you want to save at each step. Uh, that so oh yeah, the difference between steps and epochs is, so let's say you have 10 epochs in a model, and you have 1,000 batches. So of an iteration over a certain number of batches, like x number of batches, will be named as one step. So it's something like that. A step is a smaller version of an epoch. It's I mean, but it's at the end of the day, it's like it signifies like how much a model has progressed. It's a more finer way to analyze your model. So you can, for example, you can save the model at, like, let's say each 100 steps. After 100 steps, I want to save the model, and I want to test the model at these particular steps. So it will give you a finer control over how much your model learns, and like at what point it is learning what things. So it might so happen that like going over, let's say, only 10% of your data, the model learns everything. They can learn substantial amount, and like before complete, like, okay, so there are 100 data points in your data. After passing 10 data points, the model starts to overfit. So if you are doing the save strategy of epochs, saving at each epoch and testing at each epoch, you won't be able to catch this overfit, because it's like, after only one epoch the model is overfitted. What can I do? But in reality, the model was performing very well up to only 10 data points, because that is the only thing that is it was required to learn to fit perfectly over the data, beyond which it was just overfitting. So if you had done the save steps option and you're saving the model at, let's say, like 2 steps or 5 steps each, you will be able to identify the point where my model overfit, and you can like just use that model as the final model. Now again, like, it is very unrealistic for a model to fit with just to model to overfit with just 10 data points. But this is a small example to just make you understand what is the significance of steps and what is the significance of epochs. Now, like, in for this code, as this is a very preliminary introductory code, I'm doing save strategy as epochs. Like, at each epoch I'm saving, so at the end I'll have 3 models, which is at epoch 1, epoch 2, and epoch 3. But ideally, we should do steps over here. So yeah, going ahead with that. Evaluation strategy, no, because like, as you can see, there was only one train set, and again, like, I'm repeating again, since it's just an introductory code, I'm not like writing the test loop for this as well. So yeah, so evaluation strategy, no, it basically means like do not evaluate. We'll go through this in a much more detail when we'll do in the next lecture, when we'll do actually fine tune a model with results on a summarization task. So yeah, but that is for a later part of the course. Then this is trainer is equal to trainer, so it gives the model, gives the arguments, and the data set. So yeah, tokenized dataset, that is a train split of the tokenized dataset. And trainer.train, this starts training, and the model.save pre-trained. So yeah, so one disclosure, like, uh, fine tuning Llama 3.2, like, even by using LoRa, was not possible for me on my local GPU, which was which is the RTX 3050 with 4 GB VRAM, I believe. It was not possible on my local GPU. I mean, the code was running, but like, it was taking a lot of time. So like, it was practically not possible for me to run the code on my local GPU. That's why we had shifted to a server with shifted to a server with a better compute. And probably at the summarization, like in the lecture where we'll do summarization, over there also I'll be using the server for computational resources. But yeah, like, that is how things are at the end of the day. Like, sometimes, most of the times, local compute is not enough. Anyways, yeah, coming back to the lecture. So yeah, so this is save pretend. This is the like, local, like, since this code was running on the server, this is the, like, local directory of the server where I wanted to save it. Tokenizer.save pre-trained, same path. So what this does is, this saves under the same name, but inherently the save pre-trained saves it as 2 separate things. As you can see over here, automized from pre-trained, and from pre-trained is also taken from the same checkpoint. But these class make it so that, like, even when I'm loading to the same checkpoint, I only get the values of tokenizer which are important, and do not load the any model values that are there. So this is again a predefined library. Everything is run behind the scenes, so you need not worry about that much. But yeah, then okay, so this is if you want to save it locally, this is that. Another one is model.push to hub. So if you want to store your model on the cloud, like, you can use this particular method to store it on the cloud, on the Hugging Face hub. And the part to that would be your username slash whatever your preferred model name is. So I personally uh, did not do it, because, like, I did not do it, but this is the code that I did not choose to do it. This is the code which you can use to like, do it. You can push the model to hub using this particular code. um, that's all. That's pretty much it for this lecture. I'll show you the like, loss progression, not how it went. So yeah, so internally, this trainer class that does define a van db, weights and biases as well. weights and biases graph as well, like run as well. So I'll show that to you right now. But yeah, we're pretty much done for this Hugging Face lecture. Yeah. So coming to the plots now, as you can see, this is like epochs to steps plot. So as you can see, in about 3 epochs, in about approximately 3 epochs, it had about like 65k steps. So that is the relation between steps and epochs. So like up till like 1 epoch, you had like 22k steps. So that is the relationship between like train and epochs, steps and epochs. Sorry, that I was telling you about. Yeah. So this is plotting the train loss at every step that you can see, and as you can see, it's all in all, like it starts at like 3.3, then it suddenly falls to around 2.4, 4ish, and then it starts to go down and averages around 2.2, 2.3, 2.3 to be specifically, to like 2.25, something like that. So as you can see, it is going down. The model is learning something, and most definitely 3 epochs is not enough for this model to learn anything. We definitely need more than this, or we need to increase the learning rate, or like play around with other hyperparameters. As you can see, this is the grad norm is also plotted over here, and it is starting to increase as everything, like learning rate is also plotted. It starts from the value is set initially and then goes down, like approaches to 0. um, so yeah, there are like these 3 parameters is what we should be looking out for. So yeah, that's all. In the future, if you do testing as well, test at each epoch, test at a particular number of steps, then even those will be get added, like those metrics such as for summarization tasks, the question answering tasks, it would be RUG1, RUG2, RUGL, bird score, blue scores, like these scores we decide to calculate, even these will start getting logged at this particular thing. How you can access this? So whenever the model starts a run, it'll give you a link that you can like view this run at this particular link. It will be your own account and some particular checkpoint ahead of it. So you can just go to that. That's not an issue. So yeah, that is it for this lecture. In the next lecture, we'll look at summarization, like how to do summarization by fine tuning other LLMs. That will be one application oriented lecture, like application of LLMs and whatever we have learned till now, like what application of fine tuning as well. So yeah, that will be it for this lecture. I'll see you in the next lecture. Thank you.